All right, we're going to do, well, part of 5.2. So section 5.2, well, I'm going to get rid of these two. We're not going to build cubic models, and we're certainly not going to use a graphing calculator unless you have one and you want to. But this is a terrible name for what we do. Graph a polynomial function. We clearly don't just graph the functions. We also answer questions about the graph. Even before the graph is, appears, you still have to be able to answer certain questions about it. So graphs, studying the graph of a polynomial function, sure. Now, so to tell you the truth, these are almost painful for me to look through because the author just overdoes every step, every opportunity the author has to stretch this out longer than he needs to. He does it here. So I'll explain what I mean. But if you're lucky enough to have a polynomial already factored, you know what you know? You can set these factors equal to 0 and find the intercepts just like that. So if it's factored, you can find the intercepts. What else do we want to know? Well, basically we want to know the lead coefficient or the lead term and the constant term. That's it. These terms in the middle don't really do us any good. So this is the first time the author kind of overdid it. I think you could tell that this would contribute an x squared, and this would be a 3x, and if I multiply this together, I would get my first term would be 3x cubed. I didn't need to go through all of this. I mean, we could, but I don't need to go through all of this to realize what the first term is. Let's talk about why that is important. So that means this graph, with or without these middle terms, is still going to do what 3x cubed, or really just x cubed, does. And what I mean by that is it's going to leave the box in quadrant 1, and it's going to leave the box in quadrant 3. So we know that. Now, what does this for? Well, where does it come from? If I squared this properly, it would leave a, other terms, all of this actually, but it would leave a 4, and this has a 1. So multiplying those together, I get that the constant term, or a sub 0, is 4. This 4 times that 1. What that tells me is f of 0 must be 4, because all the terms with x's would be 0 when I put in the 0. So that gives me another intercept. With 3 intercepts and knowing where the graph is going to leave the box, and by the way, recognizing that this intercept is multiplicity 2, some of the things I'm saying we covered in 5.1, you might have to look at that. But since this is multiplicity 2, the only thing that could possibly happen is this, right? The graph has to have this turning point, has to touch the graph at 2 and leave the box. Then it has a turning point. I don't know where the turning point is. I might as well put it anywhere. The only thing I'm trying to avoid is putting it at that spot. I have to turn around, and maybe I might be wrong. In other words, the graph could have a turning point after. The turning point could be in quadrant 3. The sad truth is we don't know where where this turning point is, but we do know where this point is 4. So try to draw a smooth curve that captures that point, and does what? Leaves the box in quadrant 3. This is a wonderful graph. This is it. This is what we do. Why did the author spend 5 pages on this particular answer because the author kind of overdoes some of the things I just said. But let's see what he did. Found the value. So this is the wording they use on the website as well. So for large values of x, it's going to behave like 3x cubed. These other terms that I crossed out, that we might not even bother finding actually, don't really have much impact on the graph. In other words, if that were a 12 and that were a 9, I would have drawn the exact same graph. It had nothing to do with, well, that would have changed a few things up here, but if that turned out to be a different number, it would, if I'm just going on the information I had, if I still had these intercepts and I still had these points, I would have graphed the same thing. Actually, if that were a 12, it wouldn't have factored, so I kind of go back on what I said, but all right. Well, clearly if you have the function, you can actually plot points, which is something we don't generally do, but f of 0 being 4 is an intercept. We like that. Of course, they talk about the multiplicity, whether it's going to cross the graph where it was, if you recall, x plus 1/3 to the 1. The 1 was invisible. And this was x minus 2, the factor that gave us 2 as a 0. But it was squared, so that means it doesn't cross, it just touches it in the same way, y equals x squared touches the x-axis. They discuss turning points, and again, I think these are just educational opportunities. The author just wants to throw this out. Yeah, there must be 2 turning, or up to at most 2 turning points. Puts all the steps together, and you get a picture that's not much better than the one I did. No, it is better. This is a computer illustrated graph. The author actually found an extra point here by plugging in 1, y1, just because. Y negative 2 or negative 1, just because. But the author must have evaluated a few other points just to get an accurate graph. Now, sorry, I understand why the author is doing that. I'm sure student after student after student in years past had trouble graphing with just 3 points and some notion that the graph leaves the box here and here. It's a lot more comforting if you have students connect more and more and more dots, and so then they know exactly where the graph is headed. But we're not here to make this comfortable. We're here to make it relatively quick. And if you keep on doing this kind of thing, plotting the extra points and doing all that extra work, these problems are going to take you a very, very long time. All right, let's look at this one. For the first term, we're going to call it a n x to the n. This contributes x to the 1, this contributes an x squared, and this contributes an x. So putting all that together, it's x to the 4th. Just x to the 4th, no number in front of it. All right, how about the constant term? Squaring this would give you a 9. There's a minus 4 and a plus 1, so the constant term, a sub 0, is, what did I get, negative 36. I'm saying I already have this thing pictured in my head, and so should you. Okay, maybe not already, but negative 1, negative 3, positive 4. I'm just setting these equal to 0 like we did back in Algebra 1. Notice that the 0 at negative 3 is this kind of intercept where it will just touch. And the reason why I put it there is, what does 4th degree, what does x to an even number do? It leaves the box in quadrant 2 and quadrant 1. All right, so the graph has to do this. And then what? It has to come down to negative 36. That's the intercept. and leave. All right, so this is supposed to be smooth here, smooth graph, but it went through the 1, 2, 3, 4 intercepts that I found. The 3 x-intercepts we find by factors, and the y-intercept we find at a sub 0, and we're done. But they're going to ask questions about how the graph behaves. They're going to do a little more, formal analysis with the intercepts, setting each one equal to 0. All right. Well, let's just get to the, and I forget this point. Not every author does this, but this author actually plots extra points just for extra connections. I don't know if you see it. This graph is kind of the computerized version of the graph that I had on the earlier page. I certainly wouldn't have considered anything on the y-axis. Generally, we're not really all that concerned about the y-axis, but because the author plotted extra points, he found out that there, maybe where the turning point is, and even then, this was obviously done by a computer. There's no way you would just connect these dots and know the turning point was right exactly there. So even with all the extra work the author did, he's not really explaining why this computerized graph has the exact turning points it has. But in any case, that is the author's graph, and I'm going to go back to it. I know I don't want to scroll too quickly because it's awkward. This was my graph that I got, and yeah, I didn't even mark the y-axis other than I know negative 36 is down here, like below. But that's the only time I really cared about the y-axis. So what did we learn with all that extra work and point plotting? That this graph really does keep on going before it makes its turning point. But that's so unimportant to us. It's not something we should focus all this extra work on. But all right, that's it. That's all we're going to talk about in this section. The other topics in this section are not covered. So we don't do the graphing calculator and the other things. So that is section 5.2, which is also the last section of exam 1. So this is a good stopping point. I think it's a healthy set of review material and clearly some new ideas to some of you, or at least extensions of ideas that you might have done before. In other words, in a previous class, you might have done things like this, where you set those equal to 0 and find that graph, but we're extending it to something obviously more advanced. But all right, 5.2.